Purple is one of the most recognizable colors in the gemstone world, which is exactly why it leads to so many misidentifications. Because the moment a crystal appears violet, amethyst is often assumed without question. Yet in mineralogy, visual similarity can conceal completely different chemical origins. Some purple gemstones derive their color from trace elements rarely present in quartz environments. Vanadium replacing aluminum inside corundum, manganese altering crystal symmetry, beryllium appearing where few would expect it. In several cases, the element responsible for the purple color exists in quantities so small, its presence fundamentally changes how the crystal forms and how often it appears in nature, which explains why two violet gemstones can look remarkably similar, while belonging to entirely different rarity categories. Starting with a gemstone frequently mistaken for amethyst, number 10 begins now. Ranked 10th, purple sapphire. When familiar color hides an unfamiliar chemistry. Purple gemstones are often categorized quickly. Color creates confidence, and confidence often leads to assumption. Because when violet appears inside a transparent crystal, the mind frequently identifies amethyst before any other possibility is considered. Yet mineralogy rarely follows visual shortcuts. Purple sapphire forms within corundum, a crystalline aluminum oxide environment fundamentally different from quartz. And unlike amethyst, whose color originates primarily from iron interacting with natural irradiation inside silicon dioxide, purple sapphire develops when vanadium enters the crystal lattice and subtly alters the way light is absorbed. Vanadium is not commonly associated with violet gemstones. Its presence inside corundum requires a narrow geochemical window in which aluminum atoms can be partially replaced without destabilizing crystal growth. Too little substitution produces no visible color shift. Too much introduces competing hues that move the gemstone away from violet entirely. This balance occurs infrequently in nature, which is why purple sapphire appears far less often than its blue counterpart. Most sapphire deposits favor iron and titanium combinations that create blue coloration. Vanadium-dominant environments require different formation conditions, often involving trace element availability that fluctuates across geological time and pressure. Even when vanadium is present, crystal clarity may not follow. Corundum forms under conditions where structural imperfections can interrupt transparency, reducing the number of specimens suitable for faceting. As a result, gem-quality purple sapphire represents the intersection of multiple unlikely factors: appropriate trace element, presence, stable crystal lattice formation, sufficient transparency for light interaction, and perhaps most interestingly, visual familiarity works against it, because purple sapphire often enters the market carrying the disadvantage of resemblance. Collectors accustomed to associating violet color with quartz may overlook corundum specimens whose chemistry places them in a completely different rarity category. Yet the distinction matters. Corundum ranks significantly higher on the Mohs hardness scale than quartz, contributing to durability differences that influence long-term desirability. More importantly, vanadium-driven coloration represents a less common chromophore pathway than iron-based color in quartz environments. In other words, the purple color may appear familiar, but the atomic story behind it is not. Two gemstones can reflect nearly identical wavelengths of light, while forming through entirely different chemical circumstances. One occurs relatively often, The other requires trace element conditions that nature rarely repeats, which quietly explains why certain purple gemstones are evaluated differently, even before market perception enters the conversation, and why color alone rarely tells the full story. The next gemstone reveals how multiple trace elements can interact within a single crystal structure, creating violet tones that cannot be attributed to one element alone. Ranked 9th. Rhodolite garnet. When multiple trace elements compete for the same color. Not all violet hues originate from a single chemical influence. Within garnet's crystal structure, color often emerges from interaction rather than dominance. Rhodolite occupies a position between pyrope and almandine garnet, where manganese and iron coexist within a tightly bonded silicate framework. Instead of one trace element determining the optical outcome, multiple chromophores influence how wavelengths are absorbed and reflected. This internal competition produces a violet-red spectrum that can shift subtly depending on concentration balance. Small changes in elemental proportion alter the final appearance. Slightly higher iron content deepens red tones. Increased manganese contribution shifts the visual result toward purple. Unlike quartz, whose silicon dioxide lattice readily accommodates iron impurities with relative consistency, garnet forms through metamorphic processes involving higher pressures and complex mineral interactions. These environments must provide sufficient manganese availability while preserving structural stability for crystal growth. Such alignment does not occur frequently. Metamorphic conditions capable of producing gem-quality rhodolite often require specific temperature gradients that encourage mineral transformation without introducing excessive internal stress. During formation, competing trace elements influence absorption spectra across multiple directions of the crystal lattice, creating depth of color that appears more complex than a single element chromophore typically produces. Because garnet structure is more chemically dynamic than quartz, trace element distribution can vary across individual specimens. Zoning patterns sometimes reveal fluctuating chemical availability during growth, where localized manganese concentrations modify color intensity in ways difficult to replicate consistently in nature. This variability introduces another layer of rarity. Consistency itself becomes uncommon. Amethyst, while visually appealing, often displays color distribution influenced primarily by irradiation exposure and iron concentration within relatively stable quartz frameworks. Rhodolite's violet coloration, by contrast, depends on multiple elemental influences maintaining balance during crystallization. Too much dominance from one element shifts color away from purple. Too little interaction produces less distinctive hues. The result is a gemstone whose coloration reflects chemical negotiation rather than simple substitution. When multiple trace elements compete within a confined crystal structure, the probability of producing a visually desirable violet decreases significantly. Each element must occupy appropriate structural positions without destabilizing transparency or introducing excessive inclusions. Collectors often recognize this difference under controlled lighting, where rhodolite reveals layered color depth rather than uniform saturation. Such complexity does not always announce itself immediately, but once observed, it becomes difficult to overlook. The next gemstone demonstrates how certain crystal structures restrict which trace elements are permitted to enter at all. Creating violet coloration only when extremely specific chemical conditions are satisfied. Ranked 8th. Scapolite. When crystal structure allows almost no margin for color. Certain minerals impose strict limitations on which elements are allowed to participate in their formation. Scapolite belongs to a group of framework silicates whose crystal architecture leaves little flexibility for chemical variation. Its structure is built from interconnected aluminum, silicon, calcium, and sodium components arranged in a lattice that tolerates only narrow substitution pathways. When violet coloration appears in scapolite, it often reflects the presence of sulfur or chlorine-related influences interacting within confined structural channels. Such participation is not easily achieved. Many trace elements that readily enter quartz are excluded from scapolite due to size, charge compatibility, or bonding constraints. The crystal lattice acts almost like a filter, allowing only certain atomic configurations to stabilize without introducing distortions that disrupt transparency. Because the framework provides limited structural tolerance, the emergence of color depends on precise chemical timing during crystallization. Trace elements must be present at the right concentration while the crystal grows, yet must not interfere with the geometric balance required to maintain clarity. Excess substitution may cause fractures, cloudiness, or structural stress that prevents gem-quality material from forming. Even when suitable trace elements are available, the geological environments supporting scapolite growth are not widespread. Metamorphic zones capable of producing transparent crystals often involve complex chemical interactions between evaporate-derived components and aluminum-rich host rocks. These interactions must evolve gradually enough to allow ordered lattice development. Rapid environmental change interrupts growth. Insufficient trace element presence produces colorless material. Excess chemical activity introduces instability. Each condition reduces the probability of violet coloration appearing in transparent form. Compared with quartz, whose lattice accommodates iron relatively easily across numerous geological settings, scapolite demonstrates how structural rigidity limits color diversity. The rarity of violet scapolite does not arise solely from element scarcity, but from the mineral's selective tolerance for substitution. Only a small number of atomic configurations produce stable coloration without compromising optical quality. Microscopic examination sometimes reveals subtle structural irregularities, where trace elements influenced crystal growth boundaries. These features serve as evidence of the narrow chemical window required for violet formation. Collectors familiar with scapolite often recognize that transparent purple specimens represent a convergence of unlikely factors: restricted structural flexibility, limited trace, element compatibility, controlled crystallization conditions. Visual similarity to more common violet gemstones can obscure this complexity at first glance. Yet within the crystal lattice, structural discipline determines whether color emerges at all. The next gemstone reveals how trace elements can influence color differently depending on viewing direction, introducing a level of optical variability that challenges the assumption that gemstones possess a single stable identity. Ranked 7th, Iolite, when violet exists only from one direction. Rotation changes everything. Viewed from one angle, the crystal appears distinctly violet. Shift orientation slightly, and the same material reveals muted blue or nearly colorless transparency. This phenomenon, known as pleochroism, occurs when light interacts differently with separate crystallographic axes inside anisotropic minerals. Iolite belongs to the cordierite mineral group, where trace iron influences how wavelengths are absorbed along specific structural directions. Rather than producing uniform coloration across the entire crystal, iron modifies optical behavior in a directional manner. Light entering the lattice encounters varying atomic spacing depending on orientation, causing selective absorption patterns that alter perceived color. The result is not a single fixed hue, but a range of visual responses dependent on viewing geometry. Such variability introduces complexity absent in quartz-based violet gemstones. Amethyst typically displays consistent color zoning, influenced primarily by iron distribution and irradiation exposure within a relatively stable silicon dioxide framework. Iolite, by contrast, presents a gemstone whose violet identity is conditional. Color appears strongest only when light aligns with particular crystallographic pathways. Outside those orientations, violet intensity diminishes. This directional sensitivity reduces the probability of achieving stones that display vivid color in finished cuts. Lapidary orientation must account for optical axes to preserve saturation, requiring careful alignment during faceting. Even slight miscalculation may result in gemstones appearing less vibrant than the raw crystal suggests. Trace element presence alone does not guarantee desirable visual outcome. Crystal orientation becomes equally important. Geologically, cordierite forms in metamorphic environments associated with aluminum-rich sediments exposed to significant thermal influence. Iron must be incorporated within the lattice in concentrations sufficient to influence absorption behavior, yet not so abundant as to darken transparency or introduce structural irregularities. Maintaining this balance presents another rarity constraint. Microscopic structural alignment governs how effectively trace elements interact with light. Because pleochroic intensity depends on crystal integrity and internal symmetry, disturbances during formation can weaken directional color contrast. In many specimens, violet tones appear only under specific lighting conditions. Such dependence on orientation creates uncertainty for collectors evaluating rough material. Without precise positioning, the gemstone may appear less distinctive than its optical potential suggests. Yet under controlled viewing, pleochroism reveals a dynamic interaction between trace elements and crystal structure rarely observed in more common violet gemstones. Color becomes an event rather than a constant, a property revealed through movement. The next gemstone demonstrates how two different trace elements must coexist within extremely narrow chemical boundaries, producing violet coloration only when competing influences reach equilibrium. Ranked 6th. Purple spinel, when color exists only, inside a narrow chemical balance. Equilibrium rarely announces itself. Within spinel, violet coloration appears only when multiple trace elements coexist in proportions precise enough to avoid overpowering one another. Chromium typically drives red coloration in spinel, while iron tends to shift optical response toward blue. Between these two dominant influences lies a narrow compositional interval where violet becomes possible. Move slightly outside this interval, and the color identity changes completely. Chromium concentration too high, the crystal trends toward red. Iron dominance increases, the hue shifts toward blue or grayish tones. Even small variations during crystallization can redirect the final optical outcome. Spinel forms within metamorphic environments, often associated with marble-hosted deposits, where mineral reactions occur under elevated temperature and pressure. These conditions influence how trace elements distribute themselves within the crystal lattice. The structural framework of magnesium aluminum oxide provides limited flexibility for substitution, meaning competing chromophores must occupy specific atomic positions without destabilizing lattice symmetry. Such balance is not commonly sustained. Trace elements rarely arrive in isolation. Geological fluids transporting chromium or iron may fluctuate in concentration over time, introducing chemical variability during crystal growth. Each shift alters the probability of maintaining the precise compositional window required for violet coloration. This delicate equilibrium explains why purple spinel occurs far less frequently than red varieties. Red spinel requires strong chromium presence, a condition more easily achieved within certain metamorphic zones. Violet coloration, by contrast, demands moderation from multiple trace elements simultaneously. Each must remain present but restrained, influencing absorption spectra without dominating completely. Structural stability becomes dependent on chemical compromise. Microscopic inclusions sometimes record interruptions in elemental availability, where slight fluctuations alter color zoning within individual crystals. These internal patterns provide evidence of dynamic growth environments where trace element distribution evolved throughout formation. Such complexity contrasts with quartz environments, where iron impurities often produce consistent violet coloration when exposed to natural irradiation. Spinel's chemical sensitivity reduces the likelihood of uniform color emergence, increasing the rarity of stones displaying balanced violet saturation. Color, in this case, reflects chemical negotiation rather than singular dominance. When two chromophores compete within a constrained lattice, equilibrium becomes statistically uncommon. And when equilibrium itself becomes rare, the resulting color inherits that rarity. The next gemstone demonstrates how unusual mineral structures can incorporate trace elements in ways that create visual textures almost impossible to replicate, revealing how chemistry can influence not only color, but pattern formation itself. Ranked fifth, Charoite, when complexity itself limits formation. Complexity introduces its own form of rarity. Charoite does not rely on a single dominant chromophore to produce violet coloration. Instead, its appearance emerges from an intricate silicate structure containing potassium, calcium, sodium, and barium arranged in fibrous intergrowth patterns rarely observed in other gemstone materials. Within this elaborate framework, trace manganese contributes to the purple tones that define Charoite's visual identity. Such structural complexity is not easily replicated by common geological processes. Unlike simpler crystal systems that form under broad environmental conditions, Charoite develops within highly specific metasomatic environments where chemical exchange occurs between intrusive alkaline rocks and surrounding mineral assemblages. These interactions must proceed gradually enough to allow complex lattice organization without collapsing into more stable, simpler mineral forms. Each participating element must remain available at precise concentrations while temperature and pressure conditions support slow structural evolution. Disruption at any stage alters the outcome. Because multiple elements contribute to the final crystal architecture, the probability of achieving stable violet coloration becomes constrained by several variables simultaneously. The fibrous internal structure characteristic of Charoite reflects dynamic growth conditions where trace element availability fluctuated during formation. These internal patterns influence how light interacts with the material, often producing a silky or swirling visual effect distinct from the transparency observed in many faceted gemstones. Trace manganese does not act alone. It participates within a network of chemical interactions that influence both color and texture. The resulting violet appearance depends not only on chromophore presence, but on the structural environment surrounding it. In simpler minerals, trace elements often produce predictable optical effects. In Charoite, structural complexity introduces variability that resists uniform repetition. Geological availability further restricts occurrence. Commercially significant Charoite deposits remain largely associated with a single region characterized by unusual alkaline rock chemistry. Such localized formation environments reduce the number of opportunities for crystal growth even before trace element requirements are considered. Multiple improbabilities intersect: complex chemical composition, restricted geological setting, trace element participation within fibrous lattice. Each factor contributes to rarity independent of market dynamics. Visual similarity between violet minerals can obscure these structural differences at first encounter. Yet beneath the surface, Charoite demonstrates how increasing mineral complexity often reduces formation frequency. Nature favors efficiency. Structures requiring numerous simultaneous chemical conditions occur less often. The next gemstone reveals how external geological forces can alter crystal coloration at the electronic level, showing that trace element influence sometimes extends beyond atomic substitution into the behavior of electrons themselves. Ranked fourth, purple fluorite. When color forms from disturbed electrons, electrons rarely remain perfectly stable over geological time. Within fluorite, violet coloration may develop through the formation of what mineralogists describe as color centers. Structural irregularities created when natural radiation alters the normal position of electrons inside the crystal lattice. Instead of relying solely on elemental substitution, this process modifies how energy interacts with the atomic framework itself. Fluorite's structure, composed primarily of calcium and fluorine, allows certain types of lattice disturbances to persist without immediately collapsing the crystal arrangement. When ionizing radiation passes through the mineral during its geological history, electrons may become displaced from their original positions, leaving behind localized charge imbalances. These microscopic irregularities influence how light wavelengths are absorbed. The resulting optical effect can produce violet coloration that appears unexpectedly deep relative to the simplicity of fluorite's chemical formula. However, stability presents an additional constraint. Some color centers degrade when exposed to prolonged ultraviolet radiation or elevated temperatures. As a result, only certain fluorite specimens maintain saturated violet coloration over extended periods. The persistence of color depends on the ability of the lattice to preserve electron displacement without reverting to a lower energy configuration. Trace impurities may contribute indirectly by influencing how radiation interacts with the crystal structure. Small quantities of yttrium or rare earth elements can modify how energy propagates through the lattice, affecting the likelihood that color centers will form or remain stable. Because these processes require both appropriate chemical composition and exposure to specific radiation environments, Purple fluorite does not occur uniformly across all fluorite deposits. Geological timing plays a role as well. Radiation events must coincide with conditions that allow displaced electrons to remain trapped within structural vacancies. If thermal conditions later shift, color intensity may diminish. Thus, the probability of producing stable violet fluorite depends on a sequence of events rather than a single chemical variable. Quartz coloration mechanisms involving iron impurities and irradiation are comparatively well understood and frequently repeated in nature. Fluorite's color center formation introduces an additional dependency on geological history, one that cannot be predicted solely from elemental composition. Color becomes a record of environmental exposure rather than simply a product of chemical substitution. Microscopic examination often reveals zoning patterns reflecting variations in radiation intensity during growth phases. These subtle differences contribute to the diversity observed among violet fluorite specimens. Such sensitivity to geological conditions limits the number of crystals capable of preserving saturated color suitable for collectors. The next gemstone requires the presence of an element rarely concentrated in sufficient quantities to support crystal growth, demonstrating how scarcity at the elemental level can influence the existence of an entire mineral species. Ranked third, Jeremejevite, when a rare element determines whether the crystal exists at all. Boron rarely gathers in sufficient concentration to form gem-quality crystals. In most geological environments, boron disperses into fluids or incorporates into minerals that crystallize rapidly, leaving little opportunity for transparent structures to develop. Jeremejevite forms only when boron remains available long enough to participate in aluminum-bearing crystal growth without being removed by competing mineral reactions. Such conditions require unusual chemical stability. Jeremejevite belongs to the boron mineral group, where boron atoms integrate into a tightly coordinated lattice alongside aluminum and oxygen. The resulting structure differs significantly from silicate frameworks commonly encountered in more abundant gemstones. Because boron possesses distinct bonding behavior compared with silicon, the crystal must maintain environmental equilibrium long enough to allow orderly growth. Even slight chemical disruption alters the outcome. If boron concentration decreases prematurely, crystal formation halts or transitions into different borate species. If competing elements dominate the environment, structural organization may favor more stable minerals with simpler chemical requirements. As a result, gem-quality Jeremejevite remains uncommon, not merely because of limited geographic occurrence, but because the geochemical pathway necessary for its formation rarely persists over extended periods. Trace iron may influence coloration in certain specimens, contributing faint violet tones when optical absorption aligns with structural symmetry. Yet color alone does not define its rarity. The mineral itself exists only when elemental conditions align within narrow margins. Pegmatitic environments capable of concentrating boron often undergo rapid crystallization sequences, producing numerous mineral species simultaneously. Within these dynamic systems, Jeremejevite must compete with other boron-bearing minerals for available chemical resources. Such competition reduces the probability of sustained crystal growth. Microscopic examination sometimes reveals internal features consistent with fluctuating elemental availability during formation. These structural variations provide evidence of changing geochemical conditions influencing crystal development. Because boron behaves differently From more abundant elements such as silicon or aluminum, mineral species dependent upon it tend to form in fewer locations worldwide. The rarity of boron-rich environments capable of sustaining transparent crystal growth contributes directly to the limited supply of gem-quality Jeremejevite. Unlike minerals whose coloration arises primarily from trace substitution within common structural frameworks, Jeremejevite demonstrates how elemental scarcity can determine whether a gemstone species forms at all. When the required element itself is uncommon in concentrated geological environments, the probability of repeated formation decreases significantly. Color becomes secondary to existence. The next gemstone illustrates how the presence of two rarely associated elements within the same crystal lattice created a mineral that remained unidentified for decades, revealing how subtle differences in chemistry can delay recognition of rarity itself. Ranked second, Taaffeite, when a gemstone was discovered only because something seemed slightly wrong. Classification sometimes begins with doubt. For decades, certain faceted stones circulated through collections under the assumption that they belonged to the spinel family. Their appearance aligned closely with known magnesium-aluminum oxide compositions, displaying optical characteristics consistent with established mineral categories. Nothing immediately suggested the presence of an entirely different species. Yet careful measurement revealed a subtle inconsistency. Optical behavior did not align perfectly with expectations. Further analysis identified the presence of beryllium within the crystal structure, an element not typically associated with spinel. The coexistence of beryllium and magnesium within the same lattice produced structural variations significant enough to justify classification as a distinct mineral species. Taaffeite emerged not from visual recognition, but from scientific discrepancy. Beryllium rarely appears in mineral structures already stabilized by magnesium and aluminum. Its atomic radius and bonding preferences introduce constraints that limit how frequently such combinations occur in nature. For a crystal to incorporate both elements without destabilizing growth conditions, the geological environment must provide access to multiple chemical components simultaneously while maintaining equilibrium long enough for lattice organization. Such convergence is statistically uncommon. Pegmatitic environments capable of concentrating beryllium often produce barrel group minerals, where the element integrates into silicate frameworks more naturally suited to its structural behavior. The appearance of beryllium within a magnesium-rich oxide structure requires chemical conditions that diverge from typical mineral formation pathways. Trace element compatibility becomes restrictive. Even when appropriate elemental sources exist, temperature and pressure conditions must remain within ranges that permit structural accommodation without causing phase transformation into more stable mineral forms. Because Taaffeite shares visual similarity with spinel, early specimens escaped recognition. Only through refractive index measurement and spectroscopic evaluation did mineralogists identify differences revealing the presence of an additional element influencing crystal symmetry. Color in violet Taaffeite may involve trace chromium or iron interactions, yet the defining rarity originates from elemental coexistence rather than chromophore intensity alone. The gemstone exists because multiple unlikely conditions aligned: availability of beryllium, presence of magnesium-rich environment, structural tolerance for both elements simultaneously. Each requirement reduces formation probability. When rarity originates from chemical compatibility constraints rather than limited geographic supply, the resulting mineral species often remains unfamiliar even to experienced collectors. Visual similarity obscures structural distinction. Without analytical verification, Taaffeite can remain indistinguishable from more common gemstones. Such scientific subtlety contributes to its intrigue. Recognition of rarity depends on understanding chemistry rather than relying on appearance. The final gemstone demonstrates how one trace element can dominate crystal identity so completely that color becomes inseparable from the chemical environment that created it. In first place, Sugilite. When one trace element defines the entire identity of the crystal. Manganese rarely produces color with such authority over an entire mineral structure. Within Sugilite, manganese does more than influence hue. It participates directly in shaping the crystal's internal chemistry, contributing to the formation of a complex cyclosilicate framework in which multiple elements must coexist in precise structural relationships. Potassium, sodium, lithium, and iron may also appear within the lattice. Yet manganese remains the defining chromophore responsible for the saturated violet coloration that distinguishes Sugilite from more common purple gemstones. Unlike minerals where color results from minor impurity presence, Sugilite demonstrates how trace element dominance can become inseparable from mineral identity itself. Remove manganese from the chemical equation, and the characteristic purple coloration disappears entirely. The geological environments capable of producing Sugilite require unusual alkaline conditions often associated with metamorphosed manganese-rich deposits. These environments must sustain chemical stability long enough for complex silicate ring structures to organize without collapsing into simpler mineral forms. Such structural complexity introduces multiple formation constraints simultaneously. Element availability alone is insufficient. Crystal growth must occur under conditions allowing lithium-bearing and potassium-bearing components to integrate within the same structural network. Temperature and pressure must remain stable enough to prevent destabilization of the cyclosilicate arrangement, while trace manganese maintains optical influence across the lattice. Each requirement reduces probability of formation. Many manganese-bearing minerals exist, yet only a small fraction develop transparent or vividly colored material suitable for gemological interest. In numerous deposits, manganese contributes only minor coloration effects or becomes diluted by competing elements influencing crystal growth. Sugilite represents a case where manganese concentration achieves sufficient dominance to control optical identity without compromising structural integrity. Such balance is not frequently repeated in nature. Microscopic examination often reveals intricate internal textures reflecting the dynamic chemical environment present during crystallization. Variations in elemental concentration may produce zoning patterns that record shifts in geological conditions over time. These features provide evidence of a mineral formed through prolonged chemical stability within environments already limited in geographic distribution. When trace element dominance defines both color and structure, rarity emerges from chemical specificity rather than simple scarcity of raw material. Two violet gemstones may appear similar at first glance, yet one may derive color from relatively common iron substitution within quartz, while another requires manganese-rich conditions rarely sustained long enough for complex crystal growth. In such cases, color serves as an indicator of geological improbability. Sugilite represents the point where trace element presence does not merely influence appearance, but determines whether the mineral can exist at all, which ultimately reveals the central theme connecting every gemstone in this list. Color similarity does not imply chemical similarity, and chemical rarity often begins where visual familiarity ends. Some purple gemstones appear familiar, yet form under chemical conditions nature rarely repeats. Trace elements such as vanadium, manganese, boron, and beryllium quietly determine how often these crystals can exist at all. Which raises an interesting question. How many gemstones are assumed common simply because their color feels familiar? Rarity does not always announce itself. Sometimes it hides inside the smallest details of chemistry.